Okay, well, thanks so much for everyone for coming to our next GeoDAWG seminar, and hope everyone had a nice summer break. We're really excited to start this series up again this September, and really looking forward to Enrico's talk this afternoon. Just to give you a heads up, so my name is Adam Michael. I am a postdoc here at APL along with Anthony Sciola, and we're working together with Tomoko to put this series together. Just before we get into the seminar and let Enrico take it away, I just want to give a few logistical comments. Is that we will be recording the seminar as Anthony just did, and be posting the video to our YouTube channel. So please make sure to check that out so you can see this presentation again, as well as previous seminars there as well. This seminar series is held the first Tuesday of every month, and you can find the upcoming seminar speaker list on our website, which is given at the top of this page. We are taking speaker suggestions, so if you know someone, if you would like to, or know someone that will give a good presentation as part of this Yaga group, please feel free to contact us in that Google form there. And then if you haven't already, we will be sending out information such as our just to our mailing list, so please sign up to our mailing list. There things such as there's a workshop coming up that we're trying to organize in sometime in the fall, or maybe early spring or winter, and we'll be sending out a notification about that in the next month. So please keep your eyes out open for that as well. So I will pass along to Anthony now, who will introduce our speaker.
All right, thanks, Adam. Welcome back, everyone, for the almost fall series. Just some quick reminders. Please remain muted unless you're actively talking. If someone comes in unmuted, we'll try and mute them as quick as possible. And then also, Enrico is happy to answer questions during his talk. So feel free to ask him a question either by entering in the chat or raising your hand, and then we'll make sure that he sees it and we'll answer it for you. So with that, just a really quick overview. Enrico Camporeale is a research associate at UC Boulder and affiliated with the NOAA Space Weather Prediction Center. And his main research interest is on using machine learning and data simulation to study space plasma systems and geospace system. So with that, Enrico, thank you for joining us today, and please take it away.
Thank you. So I'm going to share my screen. Thanks very much for this opportunity. Let me see if this works. I'm going to stop my video just to save a bit of bandwidth. Can you see it well?
Mm-hmm. Yeah, looks good.
Okay. All right, so I'm going to talk on solving inverse problem in Geospace using PINN, even though I'm going to have a bit of an overview of other Bayesian methods before digging into PINN. Let me just move things around a little bit here. They're not in the way. Okay. So let's just get started, and I'm going to spend the first few minutes. Well, I'm pretty sure everybody is familiar with these concepts, but just to be everybody on the same page. So what is an inverse problem? And this is sort of a very general, if you like, even loose definition. So assume you have a model which we call the forward model M, that depends on a number of parameters theta, and that results in an output of interest and observable, basically Y, which is a function of M of theta, and of course can be linear model of a very complex nonlinear simulation or whatever. Assume you have a given set of observations, data. The question we're trying to answer when we solve the inverse problem is the following: what are the parameters theta such that the error between Y and D, the data and the simulation results, is minimized? So what is the theta that minimizes this error? So the best, if not the only way to solve inverse problem is by using Bayesian probability. So I'm gonna, again, just for the sake of everybody being on the same page, spend a couple of minutes talking about Bayes' theorem. This is very, very basic stuff, which is almost never touched upon in seminars and presentations. So I thought I'm going to have a few slides about this. So Bayes' theorem is has been said that is to the theory of probability what Pythagorean theorem is to geometry. And in fact, it's not, I mean, to my mind, it's not even a theorem, it's just a basic law, it's sort of a fact of life, if you like. So if you have a joint, I hope you can also see my pointer here. If you have a joint probability, so again, very general setting, A and B are just discrete events. So joint probability of A and B, again, a simple law of probability tells us that this is the probability of A given B or condition on B times the probability of B. And you can play the same definition, just swapping around B and A. So the probability of the joint probability of B and A is the probability of B condition on A times the probability of A. So now you realize that this guy on the right, on the far right hand side is equal to this guy to the left hand side. So these two in the middle are equal. And the Bayes theorem is just as simple as this, dividing basically the left hand side or both sides by P of B. So the probability of A condition on B is equal to the probability of B condition on A times P of A divided by P of B. This is a very simple but very powerful theorem or law, if you wish. So why Bayes' theorem is so important? Because, and this is very non-trivial, it allows to write the probability of A condition on B in terms of the probability of B condition of A. In other words, it flips the conditional probability. And in fact, in my opinion, well, in many people's opinion, Bayes' formula is sort of hardwired in human decision-making. So you can see this as a kind of our natural way of updating the probability we assign to any given event at the light of new information. In fact, just yesterday when I put up these slides together, I found out this, I didn't know about this. I thought, okay, somebody must have done some research showing that human actually thinking in a Bayesian way, found this science paper that in fact shows exactly that. However, there's a little asterisk here. Most of the time we get the math wrong, and this is another fact of life, that our brains do not intuitively grasp probability. It's very hard for humans to understand and to think in terms of probability, especially condition probability. And if you're not familiar with the Monte hole problem, I suggest you go and Google this. It's a very simple example, very counterintuitive probability sort of exercise. So how does the Bayesian parameter estimation works? Again, let's assume you have a model. Now I call the model, since the model depends on parameters, but also on everything else, like boundary condition, time step, whatever you have in your simulation, you just call this sort of capital M. So we want to use, again, Bayes' theorem to derive this posterior, which is the probability of M given D. So again, we start from the prior here on the very right hand side, which is the probability of parameters that enters in the model before seeing the data. So this is called the prior. You multiply this by a likelihood, which is the probability that the data is generated by a given set of parameters. And in most cases, people assume this to be a Gaussian distribution. So you just take your observation and your mod and your output result, and you write your probability in terms of an exponential, a Gaussian law. And this gives you the posterior, which is the probability of parameters after seeing the data. So condition on once you see the data, the observations. Now there are several ways to estimate this posterior. Again, we are interested in the posterior, which is the distribution of parameters, condition on data, which unfortunately is not directly accessible. So techniques exist to sample from an unknown distribution, and probably the most simple and well-known technique is the Metropolis-Hastings algorithm, which is at the base of the sort of vanilla Markov chain Monte Carlo method, which is just basically a way of sampling points from a distribution and rejecting or accepting these samples according to a simple rule. So I'm gonna now dig more into the topic of my talk, which is solving the inverse problem for the radiation belts. I assume most people in this audience is familiar with these concepts, but nevertheless, I've just a summary of radiation belt in one slide. So the radiation belt is this sort of torus or donut-shaped area around Earth, which where particles are confined. So because there are three quasi-periodic motion of electrons and particles, there are three adiabatic invariants, which are approximate constant, again, associated to each one of these periodic orbits. So there's the gyro motion, particles going around the magnetic field, bounce orbit going from one hemisphere to the other, and drift orbit going around Earth in either one direction or the others, depending on the charge. Now the drift, the invariant associated with the drift orbit is the one associated with the longest time scale, and therefore is the easiest to break. And this is sort of brings in the first, the simplest approximation we can use to study phase space density of particle distribution in the radiation belt is the radial diffusion, which is this equation here. And I like to, every time I think about this equation, I think this is a prime example of this very famous quote by the statistician George Box that says that all models are wrong and some are useful. Now let's just do some nomenclature here. So this is a diffusion equation where F is our phase space density, is basically our unknown or our quantity of interest. L or L star is the equatorial, well, it's proportional somehow to the equatorial radial distance, is our third adiabatic invariant, and it has units of Earth radii. T is a time, unit of days, and DLL is a diffusion coefficient, and tau is the electron lifetime. And this equation can be derived from quasi-linear theory, and it's intended for fixed values of the first and second adiabatic invariants. Now, I said this is a prime example of a model which is wrong but useful, and why is that? Well, first of all, why is it useful? The simplest reason why this is useful is because it follows very much the argument of Occam's razor of parsimony. And quoting again George Box in this famous paper in '76, he says that since all models are wrong, the scientists cannot obtain the correct one by excessive elaboration. So on the contrary, following William of Ockham, he should seek an economical description of natural phenomena. And also then he adds a very interesting quote and sentence saying that the ability to devise simple but evocative models is the signature of the great scientists. So this is really simple because it's computationally inexpensive, it's 1D in space. So L is our space coordinate here, plus time, of course. Yet it is non-trivial. So it's wrong, but it's useful because it's non-trivial, because it's a very rich family of solutions can be recovered when tau here is general enough. And then it's physics-based. It doesn't just come out of the blue. It is derived through a rigorous derivation from first principle. And indeed, it contains most of the physics responsible for the particle dynamics, and it has been studied and proved successful in many cases in the last probably 50 or 60 years. Now, why, on the contrary, it is also wrong, quote unquote wrong, because of course it's derived, as I said, with kinetic quasi-linear theory. So there's a large number actually of assumptions. Anytime that one of those assumptions is broken, in principle, you are not supposed to use this approximation. So the approximation does not hold. And in fact, there have been examples that I just sort of self-cite myself here, where there have been studies about non-resonant heating when this equation does not hold. And even when the quasi-linear theory works fine, there are multiple sources of uncertainties in just deriving or estimating the radial diffusion coefficients. So it's a short list adapted from this paper, which I found very interesting. For instance, there's different models for the background magnetic field. You have to take into account averages, bounce and drift averages. So there's no magnetic local time dependence. You have to take into account the azimuthal wave structure. And in fact, if you look in the literature in the last 20 years or so, there have been a multitude of different parameterization. And it's not that one is, I mean, they're all correct to some extent. They're all derived from data. and with different approximations maybe. So let's go again to the statement of the inverse problem now applied to this particular equation. Again, just to remind again, this is a simple equation where there's a diffusion, radial diffusion here, and a simple loss term. So the loss term here is assumed to pretty much capture everything which is non-diffusive. So everything which is not captured from the first term, so you can sort of plug into this second term, assuming you know how to describe the lifetime tau. So the question is, what is the optimal choice of, so there are two free parameters here, DLL and tau. What is the optimal choice of parameters that makes the result of the diffusion equation most consistent with data? Once again, this is an inverse problem, which is much harder to solve than the forward model. And the simplest reason is that oftentimes the inverse problem is ill-posed. There's no unique solution for the inverse problem. So once again, the standard statistical approach is using Bayesian parameter estimation. We have done this in this paper in 2019, published by a postdoc of mine back when I was in Amsterdam, in the Netherlands. So why does it make sense to use a statistical approach? Again, because the underlying model is wrong. There's not a unique solution. So we are looking for a distribution of parameters. So that's why it makes sense to go into a statistical description of the inverse problem. This has been a classical, very classical topic in geoscience, but I believe it's still not yet a mainstream approach in space physics to use a Bayesian parameter estimation. And also has to be said that it's very hard it becomes harder and harder to apply this in higher dimensions. So here we'll just stick to 1D, so we can actually do a Markov chain Monte Carlo run with this 1D simulation, but it's probably not feasible in higher dimensions. So those are just a quick glance of the result. This is not really the focus of the talk here. I'm going to talk about PINN in a second, but just to show some results. So we chose this sort of parameterization for the DLL and tau, which are sort of standard. If you can see, the DLL parameterization is very similar. It's indeed the same as the Broughtingham and Albert parameterization. And if follow, we decided a fairly general parameterization for tau. On the left hand, there are similar parameterization from the literature, from this paper by Orlova. And this is the result for DLL. Again, you have A, B, and C here, which are the free parameters from which we seek the posterior distribution, and these are the posterior distribution for these three parameters. And you can see comparing with values by Broughtingham and Albert, we have a double peak distribution here, for instance, where Broughtingham and Albert just gives a value of 0.5. So the result is actually pretty divergent from Broughtingham and Albert. It's closer for the value of B, which is pretty close here to the Broughtingham and Albert value. And C also gives us a fairly different value. And in fact, you can see here in the plots for different values of KP, how our solution in red differs from the solution by Broughtingham and Albert. Now I'm picking Broughtingham and Albert here because it's, in my opinion, is the most used parameterization for radial diffusion if you look into the literature, although it's kind of 20 years old. Now let's put aside from a moment the Bayesian approach. I just wanted to mention it to sort of give a more complete talk, because that's a very important topic in inverse problems. But the focus now is really on a completely different approach I'm gonna talk about for parameter estimation based on this paper, which, as you can see, I highlighted here. This is only 2 or 3 years old, already got 3,000 plus citations. So this already give a sort of hint of how important this method is about physics-informed neural networks. So what is a physics-informed neural network, or PINN in a nutshell? It's a very, the beauty of it, in my opinion, is that as often happens with very powerful methods, it's also very simple. So what we want to do is to include we want to solve a partial differential equation. We want to, so how PINN works is that you include, so in this case, it's this guy here in a square bracket. We include this equation in the cost function of a neural network. So the cost function typically will only be this guy here on the right-hand side, which is the difference between the model F, the output of a neural network, and observation, and you take some sort of L-square error. So this is the standard term in your cost function. You add this other term, meaning that you can think of this as a regularization term in a sense. You want the solution also to be the output of the neural network also to be a solution of the PDE. So the trick under the hood here is called autodiff, or automatic differentiation. It boils down to the fact that all derivatives are computed exactly using chain rules in a neural network. In other words, no matter how complex or how deep a neural network is, the output of a neural network is always an analytical and differentiable function. And you can differentiate, you can take all this derivative, df over dl, df over dt, exactly at any given point. So PINN, in a sense, is both a gridless method to solve a PDE, so you can use this as a forward model to solve a PDE on a set of points, which are not on a grid. Is a sort of gridless or meshless method. And it is also, and this is the way we're going to use it here, a way of estimating the coefficients of a PDE for an inverse problem. So how does this work for inverse problems? So let's talking again in sort of a very general terms. Let's assume you have a PDE in this form, df over dt, so where f is a function of space and time, plus a nonlinear term h, which is again function of f, and some free parameters d and c. You can have as many as you want here. So what we do is the following. Assuming you have two free parameters, we train 3 independent neural networks. The first outputs f, the second outputs d, and the third outputs c. These neural networks only take as inputs space and time in a given domain. And then the way this works is that you plug these 3 guys, f, d, and c, into the loss function, which again is a standard loss function with the error term here, plus the residual of the PDE. And when you do the training and you back propagate the errors in each one of these neural networks, what it comes out is that you get the optimal f, optimal d, and optimal c that solve the PDE and minimize the error with respect to the data. So every time I've presented the idea of PINN, I've realized there are some misconceptions about it. So I'm just putting my forward some question not to ask, or in other words, some clarification about PINNs, because oftentimes somebody thinks, I mean, how can you predict phase space density simply as a function of space and time? So, because as I said, the only 2 inputs that go into the neural network are, well, space in our case is called L and T. Now, the thing is that I'm not really predicting anything, or not yet now. We'll go, if I can get to the last part of my talk, I'll show you how to do predictions. But the way of thinking about this is that the neural network is a universal function approximator, which means that if you give them enough data and enough complexity or enough number of weights, any function can be fitted exactly on a finite number of points. So the way of thinking about this, in my opinion, is that the PINN is just a way of regularize a neural network. So among the infinite number of functions that fit your millions of data points, the PINN chooses the one, or the few, if you wish, that also approximately solves the PDE on a set of points. So again, it regularizes your solution such that the output of a neural network not only fits the data, but also solves a PDE. And if you have any question, please interrupt anytime. Now, there's a big caveat here when I try to apply PINN to this equation for radial diffusion. As I said at the beginning, this is on the top is the standard equation for radial diffusion. You immediately recognize that, and the one I wanted to approach this is to allow DLL, so to kind of get rid of any parameterizations the way it was done in the literature in the last 20 years, but allow DLL and tau to be very general function of space and time. And if we do that, if you allow DLL and tau to be too general, this becomes strongly ill-posed to the point that it cannot be solved as an inverse problem, because you can realize very quickly, if somebody gives you a general function for DLL, you can find the corresponding tau that actually solves this equation exactly. So there are infinite combinations of DLL and tau that give the same result. So what we decided to do instead is to get rid of this loss term, which we find to be too general, and to constrain the equation in form of the drift diffusion form of Fokker-Planck equation. In other terms, instead of this f over tau, we have a drift term where we use a drift coefficient c, or an advection term, if you like. Excuse me. So this is also ill-posed as an inverse problem, but it's much more constrained now, and it can actually be solved. And also, this doesn't, if you wish, this is also rigorous because you can derive, I mean, this is a general form of, it's a more general form of the Fokker-Planck equation with respect to the first one. Now, just going to mention a few. Now, of course, after we derive our model based on PINN, we're going to compare with some other baseline models. So we picked up these three popular schemes in the literature: Brattingham and Albert, Oziki et al., and Ali et al. For DLL. And for tau, there is this is pretty much the only parameterization I've seen in the literature, introduced by Spritz et al. in 2005, also being used more recently by Drozdov, where basically you split tau into two regions, depending on whether L is inside or outside the plasma pose. Plasma pose location is estimated empirically using a formula in this paper. And this is just a detail of how we solve the forward model with a conditionally stable scheme. Now, also, because before going into the results and the details, let me just pause a second to define some errors we're going to use later. These first two errors are actually taken by well, I should have put the reference here. A very nice paper by Steve Morley 2 or 3 years back. The first one on the left is a measure of accuracies, the percentage symmetric accuracy. One on the right is a measure for bias, symmetric sign percentage bias. You can, okay, there are some details here of how things are defined. Basically, F and F hat are respectively the model output and the ground truth, or the data. And then we use if you wish, a simpler relative error of the log of phase space density, where P50 here is the median value. Okay, let's go on to the data. We've used 4 years of data from Van Allen probes. So this is for, again, it's a radial diffusion. So it's for fixed values of mu and k, first and second adiabatic invariants. This is the full data set, is about 500,000 data points. Sort of arbitrarily, if you wish, we split these 4 years of data into a training and validation, taking the first 3 years, and the test data, taking the last 1 year of data. And what is shown here is the typical way of showing the log of the phase space density with a color map. And you can see that it ranges quite widely from 10 to the minus 11 to 10 to the minus 4. And you can also see there are sharp features which are related to injection of particles at the boundary, or storms, and all of that. So what we've done is the following. Since, well, for 2 reasons: because inverse problems are ill-posed, so there's no unique solution, but also neural networks themselves are sort of stochastic animals. Every time you train a neural network, you can get a slightly different answer, because they are randomly initialized. So what we've done is the following: we have trained the PINN 20 times, and then we calculated this epsilon, this relative error, and we picked up the best 5 solutions in this ensemble of 20. And what is shown here is, on the top panel are the diffusion coefficients, DLL, and on the bottom the corresponding drift coefficient, and those are the best 5 solutions that gives us the smaller error. Basically, you can see that maybe the sort of general features are the same among these 5 solutions, but the fine details might actually vary. And this again comes to the fact that the solution is not unique. But what we've done at the end is the following, which is maybe the most naive approach. Since we want to use a single set of diffusion coefficient and drift coefficient, we just averaged these top 5 in our ensemble. And those figures here show exactly that, the mean or the average. And what is shown on the left is the relative error on the horizontal axis versus L. So here the error is taken for a fixed value of L. So it's the median values for that given L. Different colors here are for different parameterization. The 5 black line here are the 5 results for the PINN, and the red is the result for when we use the mean of these best 5. And this is itself is non-trivial. The fact that if you just average out the diffusion coefficient, you get a diffusion coefficient that then gives you a similar error. And then, of course, this might not be so surprising because this is, I mean, the result of the PINN, this black line, are not so surprising because this is on the training set. So the goal of the PINN is really to minimize, sort of minimize this error. So this works much better than all other parameterizations. But the bottom line here, the point for you know, the food for thought, if you wish, is that at the end of this procedure, we get diffusion coefficients and drift coefficients at any given point in space and time. And this is really the gold mine, or the diamond mine, if you wish, here for data mining, because all of the physics, again, assuming that this model is valid for your study, all of the physics is sort of embedded in these two coefficients here. So all the information of interest is in these two coefficients, so, which I find very, very interesting, because we have now access to this information in space and time exactly. So the next step, what we've done, is a statistical analysis of those coefficients, and you can spend a lot of time trying to do this and figure out how to do, what's the best way of doing it. So what is shown here on the left is the distribution of the diffusion coefficient DLL as a function of L. So again, if you take a horizontal cut here for at any given L, of course you have a distribution of DLL in time. This is what is shown here as a gray area, where actually this is a 25th to 75th percentile. The median value at any given value of L is this orange line. And then what I've superposed here are the DLL, just as a line which is proportional to L to the 10. The reason being that L to the 10 is the parameterization taken by Brottingham and Albert. You can see that it works fairly well at small L, but then it deviates, and maybe L to the 20 is more appropriate at a larger L. Another way of doing a statistical analysis of these coefficients is on the right-hand side, where and this is a bit hard to digest at first sight. So this is a rank distribution of the diffusion coefficient. What it means is the following. So for any given value of L, so here you take a vertical slit here, the darkest values is the rank number 1, which means that most of the, so basically we be in the distribution here, and most of the values end up in rank 1, then comes the second one, third one, and so on up to, up to 20. So you can see sort of the trajectories, if you like, of this diffusion coefficient as a function of L. And what is interesting is that if you do the same exercise for C, the drift coefficient, you can see pretty clearly, well, there are different regimes, different parameters, sort of plateaus for L larger than 3.5, say. And here there are obviously two different, there's almost a bifurcation. So C can even live in this area, like 10 to the minus 2, or much larger, and there's nothing in between. So I find this very interesting and maybe worth further investigation. And if you look at the percentile and median, again, of course, the error becomes much larger here. And there are, again, these two different regimes. Then the next step in our investigation is a feature selection. And this is a term taken by sort of the machine learning community. What it means is to try to understand the drivers, or the most important inputs that you can use to parameterize DLL and C. And what we have done is to use a fairly simple model, which is called the backward elimination method based on generalized linear model. So how it works is the following. We selected, can't remember now, maybe 10 or 12 different inputs, like L, of course, the value of the PSD, the boundary condition, KP. Now remember, KP is all of the parameterization in the literature use KP as the most important driver because it's the way they parameterize changes in time and in geomagnetic activity. So boundary condition on the upper boundary, lower boundary. This sum here is the average along any given L. So we chose 12 of these features, and then the generalized linear model calculates a model where you combine all of these up to a second order term. And then what you do with the backward elimination, so if you use all of the coefficients, you end up with maybe with 70 or 80 terms. You train a linear model and you get R square up to 0.96, and then you start to get rid of the least important terms one at a time until you get only to one term. And you can see here that even just using L gives you R square equal 95, meaning that L is actually the most important parameter to determine the diffusion coefficient. Similarly for C, even though the numbers here are a bit smaller. And now I've circled here KP because again, KP is the most important parameter in all the parameterization here. But what I find out doing this feature selection is that only ends up being what is it, sixth in this for DLL, and it's not even there for C. So this gives us hope as to, we can maybe parameterize these two coefficients without even using KP. Now, the next step after we have learned how to select features is, of course, and that's what we're interested in, can we forecast unseen data? And this is a bit, okay, there are a few details here, but basically what we've done is the following. We need to learn how to generate DLL and C. So of course, the PINN gives you these two coefficients in your training set, but you want to have a mechanism to generate these sort of on the fly for any given condition. So we train an ensemble of decision trees, which is yet another machine learning method. It uses gradient boosting, where we use only these 1, 2, 3, 4 inputs. And again, the important thing is that we do not use KP. So the inputs is L, the log of the phase space density, which is F, and boundary conditions, and some running average of PSD over L. And we use these inputs to predict DLL and C. Now, a bit of a numerical or theoretical caveat here, if you wish, is that using PSD, we found that this helps very much into determining DLL and C, although this makes the problem nonlinear, right? Because once you have decided that DLL and C are function of PSD, the problem is nonlinear, and numerically, for instance, you can use a predictor-corrector method to solve this. It's not as simple as for the fully linear case when DLL and C are only function of space and time. So to summarize, this is our parameter estimation pipeline. So the first step is to assume that the physics obeys some kind of equation, and we have chosen the Fokker-Planck drift diffusion equation with two free parameters, DLL and C. Then we train the PINN on Van Allen probes data, and the PINN gives us the optimal coefficients which are valid in this region of space and time, so 3 years in time. And I didn't mention our domain in L goes from 2 to 5.5, so it's fairly restricted if you wish. We don't go up to L equal 8 or so. So these are the output of the PINN, again with this ensemble and averaging procedure. Then once we have this, we can derive the feature, do feature selection, so derive the feature which are the most important to parameterize DLL and C. And then we train a different model that predicts DLL and C at any given time, any given condition. And then once we have this ability to predict DLL and C, we can plug this back in our forward model and solve the equation with what I call the PINN discover and machine learn coefficients. And now finally the test, the results on the test set. This is so on this plot on the right, again, there are the three parameterization, Brattigan and Albert on top right, Ozeki and Ali on the bottom, and our results here on the top left. And what is shown as a color map is the relative error here, point by point. You can see that it's much smaller than the other two parameterization. And in fact, if you do again this exercise of taking the median value at any given point in L, the result is the black line, which is mostly smaller, or I would say comparable in some region at L equal 3 to the other parameterization. So this is it's definitely a more accurate description of diffusion or transport, if you like, of electron in the radiation belts. And then one next step or last step, if you wish, is what I like to think as a final frontier here, is doing all of this in an interpretable way. So what we've done is the following. I mean, so far I have described things in sort of, with machine learning, but in a opaque or non-interpretable way. And the weak chain, if you wish, was this model here that predicts DLL and C at any given time using a fairly complex machine learning method. So what we've done is to get rid of this step, and instead of doing this, parameterize DLL with the simplest, possibly what is the simplest approach, which you can see already from this plot that I showed earlier. The median curve here can be approximated fairly accurately with a cubic interpolation in log space. So what we have done is as simple as this: just introduce this parameterization where the log of DLL and log of C is a cubic polynomial, so it's only function of L. Now, what is interesting is that once you make this assumption or this parameterization, if you wish, and you plug this back into your forward model, the forward model becomes parameters free. So it's only now dependent on boundary conditions, because DLL and C are function of L only, and you can work out the math and write this as a simple equation with no free parameters. And those are the results in this case, where again DLL and C are function of L only, using these other two metrics that I introduced earlier, the accuracy and bias. Now it's a bit crowded here, but what you can see is that the black line, which is the result from PINN derived cubic feet, is smaller or comparable to the blue and red line, which are the Bradigan and Albert and Ozeki parameterization. Here the results is shown with error bars as well. And same goes for the bias, where bias comes with a sign, so positive and negative are in solid and dashed line. The last step I wanted to talk about is, once I sort of highlighted this before, once you have this knowledge about the coefficients, you can do all sorts of things. One of the things that comes as a sort of a side product of the PINN is automatic event identification, which means that you have your residual of the PDE, and you can see point by point in your domain in space and time how large that residual is. Which means that when the residual is large compared to other points, it means that the drift diffusion equation, or the assumption you made that the physics obeys that equation, is violated. The physics, the neural network cannot find a solution that solves very well that equation. This is what is shown here with some color, sort of saturated color. So the yellow region here are the regions where the PINN cannot solve very well the PDE, compared to other regions. And then what we have done here, shown by this red dashed line, are 12 or 15 times what we call this an event. So basically, those are the times when these the residual of the PDE falls in the 99th percentile. So this is our sort of the outlier with respect to all other points. And this is a way of automatically identify events, because what it means is that during these times, something else was happening that does not follow the drift diffusion equation. And the simplest thing to think about is nonlinear effects. So this is the list of events. And then what I've done fairly quickly, to be honest, not spending too much time on this, once we have identified those events, I tried to look into the literature whether some of those events have been studied already. And in fact, the majority of them have been identified in a more human-based way, if you like, a more traditional way, where somebody actually looked at the data and figured out that something peculiar was happening. So those are the papers in the literature associated with those events, like CME, storm, dropout events, and so on. There are some for which I did not find anything in the literature. So maybe either I missed those, or there might be something else worth a publication to study. Okay, I think I've come to the conclusion of my talk. I guess I ran a little bit, but this leaves maybe a few minutes for questions. So in my opinion, PINNs, physics from neural networks, is a game changer. Well, not in my opinion. You know, this was you know, if you saw these 3,000 citations, it really is something happening in applied math. But in my opinion, the best way we can use it in our community in space physics problem is to solve inverse problems. And here I just show sort of a use case, which is the derivation of diffusion and drift coefficients for radial transport for electrons in radiation belt. So as I said, you can do a whole lot of things with PINN. You can assess when your assumption of the quasi-linear theory are not valid. So doing, again, automatic event identification. You can, I didn't show this, but it's in the paper. You can redefine electron lifetimes. So you can take this drift term and sort of write that, redefine an effective electron lifetime based on that drift term. You can improve the accuracy in either nowcasting or forecasting. The important point here is that you don't have to use future KP values, which is the, in my opinion, is the weak chain of using this model for forecasting, because basically it just shifts the problem into forecasting another quantity, namely forecasting KP in the future, and we don't want to do that. And then the last point, which I find very interesting, is that we can reparameterize diffusion and drift coefficient, which is probably the simplest and most interpretable relationship, which is just a cubic fit. So this is the paper just came out last month in JGR. And then to conclude, I promised Tomoko to have an announcement page. So we're going to have a very dense session at the next AGU in December in Chicago. It's a nonlinear geophysics session called Machine Learning in Space Weather. We ended up having 4 oral sessions plus 1 poster session, total of 82 abstracts. So I'm pretty sure you can find whatever is of interest for you in one of those sessions. And also that is still open until, I think the deadline is 31st of December this year, but might be probably extended. Call for papers for AGU journals, a special section called Machine Learning in Heliophysics. You can submit a paper in one of these 4 journals: Space Weather, JGR, GRL, and ESS, and select this Machine Learning in Heliophysics special collection. Thank you very much, and I'm done with this. I'm gonna stop sharing.
Thank you, Enrico.
All right, thank you very much, Enrico.
Great. Yeah, go ahead.
Yeah, very interesting. I was just going to ask if anyone has any questions for Enrico.
Yeah, I've got one.
Yeah, go ahead.
Hi, Enrico. Very good talk. Thank you. It cleared up several things for me as far as doing inverse problems with PINNs. I have a question in your discussion of your loss function or cost function. I didn't see any mention of weights for the different terms, for the residual term from the equation, the residual from your boundary conditions, and the residual from your parameter estimations. Did you use a weighted loss function?
Yes, that's an excellent question. Looks like Zoom is not responding to me right now. I can't do anything. Stop sharing, or, well, can't even start the video. Okay, anyway, let me try to address that. So there is a weight. So there are these 2 terms in the loss function. And I mean, the point is that upon convergence, these 2 terms should be small enough or equally small. But during the training, you might want to put a little weight in front of one of the 2. And the strategy that I've seen works better is the following, which is starting with a sort of traditional neural network where you just try to reduce the residual, the error with respect to the data, and then sort of iteratively increase the term corresponding to the PDE.
So you're using dynamic weights?
Yes.
Oh, cool.
Yeah.
Okay.
Yeah,
Thank you.
I've played a little bit with many things, spent a lot of time, and I found out, I mean, there's no strict rule, but I found that is the most efficient way to change that weight dynamically. You can do like 50,000 epochs, 10,000 epochs, whatever you want with a given number, and then change it, increase it slightly. That's again,
That
it's
would be
heuristic, if you like, a heuristic rule, but it seems to work.
in the cases that I've looked at in the past, the weight has varied dramatically over the space 0 to unity for the boundary conditions, depending on the equation that I'm solving. And I'm trying to come up with a way to sort of tune that automatically. It sounds like dynamic weights may be a good way to do that.
Yeah, boundary condition is a different issue though. But on the boundary, what I do is to completely neglect the PDE. So on the boundary, you enforce that the data is consistent with the, I mean, the neural network output is consistent with the data only. You don't care about the PDE.
I think I need to talk to you more about this, but I don't want to monopolize the time
Okay,
now. I'll send
sure.
you a message.
Okay, yeah, be happy to.
I have a kind of related to question about cost function. Is that okay, Enrico? So you have two blocks, right? So two quadratic term for observation, and then the other one, you know, for PDF. Looks like you are actually just, am I right, that taking a tendency, PFT, so looking at the tendency of flux with this, then you square it, or do you have prior information incorporated into it? Do you use prior? Or could you explain a cost block a bit, like second term, physics term? So you're basically putting a constraint in terms of how the states evolve. So it has to follow the PDF. So like maybe you could explain like a bit.
Yeah.
Like,
so what you do is to train. So you have your domain in space and time, and you sort of feed the neural network the full domain. Of course, I mean the neural network reads a batch of these points at any given time. But so there's no, in a sense, there's no. I guess that's what it's different with respect to data simulation. Okay, there's no concept of time here. I mean, time is just a variable in your domain. The neural network just takes any given point, the value of space and time at that point, and feeds and uses this as input. So what it does is to find a function which is simply a fitting function, which is a simply function of L and T.
Yeah. So, but then you had this, the whole point of PINN is that have constraint coming from physics, right? Coming from PDE. And then what is actually doing is that sort of constraint, like make sure that the evolution of state is following that according to PDE.
Yeah, and again, the crucial point is that the all these terms you have in your PDE, the F over dt, the F over, I mean, all the terms in the PDE are computed exactly with no approximation on any given point in space and time. So what you do in the cost function, or basically when you do the back propagation, is that the neural network can calculate the F over dt at this given point and can change the weights during the train such that the whole PDE residual is as close as possible to zero. That's where you're enforcing the physics. So again, it's the way I think about it is that you're fitting as usual. You have a neural network that fits your data point, but then there's an extra constraint that this F, the function that comes out of the neural network, also minimizes the residual of the PDE. So it's a regularization term, if you like.
Yeah. I understood. So like you got the question, because I always like, what's the difference? I always get the question from other end. What is the difference between, especially approach like you're using right now, PINN, and then data simulation, because it has data and it has a model. And then I think so prior, as you said, it's not there, right? You don't use it, but just to just really more data is the one that really, I mean, physics. Yeah.
In fact, I mean, the way I see it is that PINN, even though I talk about Bayesian methods at the beginning of my presentation, but this is not really a Bayesian method. It might be done in a Bayesian way if you have a Bayesian neural network, maybe. But I believe this is people are working on this topic. The major weakness or constraint, if you like, is that you can solve. So this is not a method that allows you then to solve your equation or to march in time. You have you solve the inverse problem for the coefficients in your domain in space and time. And this doesn't allow you to extrapolate further in time or in other points in space. So it only works for the domain you have used in your training, right? And that's why I come up with this sort of elaborate way of parameterizing the diffusion coefficients for any future, for any time, basically.
Yeah, thank you for putting that in a context. And then, are you a bit afraid or, concerned about overfit? I think in general.
Concerned about what, sorry?
Overfit, because it's a really, overfit of parameter that I guess I don't know. I think maybe it's not fair, not just this, but like in general, I guess.
Yeah, it's an interesting point because the usual concept of overfitting here, I don't think really applies because you, in a sense, you do want to overfit. And then the way around it is in a sense is to doing this ensemble technique. So instead of when you train one neural network, you just get this one result that works maybe very well for the domain. Again, it's not able to extrapolate, but it's not unique. So then you train another neural network, you get a slightly different result. And then again, the simplest approach I could think of is just take the average of those, and it seems to work fairly well.
That's how you are sort of addressing that.
Yeah.
Okay. Yeah, thank you, Enrico. Yeah, I don't want to also take much of your time, and then maybe others have questions. Please unmute and then just go ahead, ask questions. It's your chance. Okay.
It means everything was crystal clear.
I guess I guess it's recorded. So stop and play. I understand what he's doing, but it's a great result. I really like that. That's connected to also informing.
So maybe just mention this next step we're gonna try to tackle is to move forward. As I say, this is the 1D approximation, which is is simple and nice, but it's an approximation. We're trying to move forward with trying to solve a 3D diffusion equation with cross terms and whatnot. So diffusion in energy and pitch angle as well, and we'll see whether one can use PINNs there as well.
I have a quick question, or maybe that's not quick, but I don't have a lot of experience with machine learning, so I guess I was wondering if you could explain how you get a different solution with each ensemble.
Yeah, no, it's pretty simple. I think it's built in the way neural networks work, in the sense that you start with a random initialization of your weights, and you try to, so neural network basically solve an optimization problem, right? Through this process of backpropagation, iterative process, you try to adjust your weights in your neural networks such that whatever cost function you have is minimized. Now, depending on, and oftentimes these cost functions are non-convex, very, they depend on millions of parameters. So you end up on a local minima. So depending on where you start with your minimization process, which means how you initialize your parameters, you might end up in different local minima. And this gives you basically different, equivalent, but different neural networks that give you slightly different results. I don't know if that answers it.
Yeah, cool, thanks.
Okay. So. And so, Adam, yeah.
Yeah, well, we'll just wrap it up, but thank you so much, Enrico, for such a wonderful talk and for kicking off this the fall series of our GeoDAWG seminar. Please be on the lookout on our website for the next upcoming talks. Next month in the week before, we'll make sure to put this presentation on YouTube so you can go back and rewatch that again if you want. So thank you, Enrico, again, and looking forward to seeing everyone in a month.
Okay. Thank you, Enrico. Thank you.
Thank you.
Thank you
Thank you, everybody.
everyone for coming. Bye.